There is a moment coming, not tomorrow, not in any human lifetime, not even within the reign of the stars themselves, when the last solid world in existence will drift alone through a universe that has forgotten how to make anything new. No sun will warm it, no light will reach it from anywhere. The galaxies will be long gone, their stars having burned out one by one across trillions of years, their embers cooling into dark, invisible objects that do nothing but fall slowly toward each other in the black. The universe will still exist, technically. Space will still be there. Time will still be passing, but everything we might call activity, everything that burns, everything that shines, everything that moves with purpose, will be finished, except for this one world, this one last planet. And what makes this strange? What makes it worth spending the next 2 hours exploring together is not simply that such a world will exist. It is that we can actually work out what kind of world it will be. We can trace the logic of how the universe ages, follow the chain of physics that governs the death of everything, and arrive, step by step, at a genuine description of the last solid object that will exist before the universe transitions into something so alien that even the word dark feels insufficient to describe it. That is what this documentary is about. Not just the end of everything, but the last thing standing before everything ends. To understand it, we need to go on a journey. We need to understand how stars die, how planets survive without suns, how the universe itself ages across timescales so enormous that our usual language for large numbers begins to fail. We need to enter a realm of physics where processes so slow they are practically motionless are still technically ongoing. And we need to follow the thread of logic from the world we live in right now, tonight, to a world so far in the future that the distance from the Big Bang to today looks, by comparison, like the blink of an eye. Let's start where all of this begins to make sense. We do not usually think of the universe as something that ages. It feels permanent. The stars seem fixed. The galaxies, for all practical purposes, do not appear to be going anywhere. But the universe is aging. It has been aging since the moment it began. And the evidence for this is something you can see on a clear night with nothing more sophisticated than your own eyes. Look up at any star, any of them. What you are watching is a controlled explosion, a sphere of gas so immense that its own gravity is constantly trying to collapse it, and the only thing preventing that collapse is the energy released by nuclear fusion at its core. The star exists in a state of balance. Gravity pulls inward, fusion pushes outward. The star holds its shape. But fusion is not free. Fusion requires fuel, and every single star in the universe, every one of the roughly 200 billion trillion stars that current estimates suggest exist across the observable cosmos, is spending that fuel right now, every second, every hour, every year. The clock is running for every star simultaneously, and all of those clocks are counting down to the same eventual outcome. The fuel runs out. This is not a speculative idea. We have watched it happen. We have catalogued the ruins of stars that have already completed this process. The white dwarfs, the neutron stars, the black holes. And we understand, in considerable detail, the sequence of events that carries a star from its ignition to its end. The universe is not an eternal machine. It is a machine that began with a finite supply of raw material, and it has been consuming that material ever since. The clock started with the Big Bang. That was approximately 13.8 billion years ago, and the amount of fuel the universe began with, the hydrogen primarily, which is the fundamental ingredient for stellar fusion, has been declining ever since. New stars form, yes, but they form from gas that already existed. The universe does not manufacture new hydrogen. What it began with is all it will ever have. And a significant fraction of that original supply has already been converted into heavier elements and locked away inside the corpses of dead stars, where it can no longer participate in the business of making new suns. This is the first thing to understand about cosmic aging. It is irreversible. The universe has a direction. It is moving, on the largest scales, from something complex and energetic and active towards something simpler and quieter and darker. The question is how long that journey takes, and the answer involves numbers so large that we need to approach them carefully, or the mind simply refuses to accommodate them. Let us spend a moment building the mental tools we will need for this journey, because the timescales involved in the death of the universe are not merely large. They are large in a way that requires a different kind of thinking. Consider what 1,000,000 years feels like. Anatomically modern humans have existed for roughly 300,000 years. 1,000,000 years is more than 3 times the entire span of our species. 1,000,000,000 years is 1,000 times larger than that. And 1,000,000,000,000 years, a number we will use casually before this documentary is finished, is 1,000 times larger still. The universe is 13.8 billion years old. 1,000,000,000,000 years is roughly 70 times the current age of the universe. That number, by the time we reach the era of the last planet, will feel like a brief introduction to a much longer story. Cosmologists who study the far future of the universe have developed a notation to handle these spans. It is called the cosmic decade system, and it works as follows. Instead of writing out the raw number of years, you write the power of 10 that represents it. The current age of the universe, 13.8 billion years, is approximately 10 to the power of 10. That is 10 billion years. This is Cosmic Decade 10. Cosmic Decade 14, 10 trillion years, is roughly when the last of the ordinary stars will exhaust their fuel. Cosmic Decade 15 is when white dwarfs begin to cool significantly. By Cosmic Decade 37, something remarkable happens that we will return to later. For now, the number to hold in mind is this. The story of the last planet takes place in a cosmic era so remote that if you tried to write it out in ordinary digits, the number of zeros would fill more pages than there are atoms in the observable universe. We are going on a journey to a place beyond the reach of ordinary imagination. But we are going to follow the logic, step by step, and arrive there honestly. To understand what will be left when the stars are gone, we need to understand precisely what happens when a star dies. Because not all stars die the same way, and the manner in which a star ends its life determines what, if anything, it leaves behind, and whether any planets associated with it survive. The key variable is mass. Massive stars, those roughly 8 times or more the mass of our Sun, live spectacular but brief lives. They burn through their fuel in tens of millions of years, not billions, and they end in supernovae, catastrophic explosions that release more energy in a few seconds than the Sun will emit across its entire multi-billion-year lifetime. These explosions are powerful enough to destroy any planets that orbit the star. Whatever was there is gone. The remnant left behind is either a neutron star, an object roughly the size of a city, but with the mass of the Sun, spinning sometimes hundreds of times per second, or, if the star was massive enough, a black hole. Neutron stars are extraordinary objects, but for the purposes of our story, they are dead ends. They cool. They slow their rotation over billions of years. They become cold, dark, dense objects that contribute nothing to the cosmic environment except mass and gravity. Any planets that might somehow form around them in the aftermath of the supernova, and there is evidence that some do, inhabit an environment so irradiated during the explosion that habitability is essentially a moot point. Black holes are even more final. They are not objects in any conventional sense. They are regions of space where the geometry itself has been permanently altered. They grow. They do not cool in any meaningful way on astronomical timescales. They will still be here, in a very real sense, long after every star has burned out, patient, dark, and vast. But the more common fate, and the one that becomes relevant to our story, belongs to stars like the Sun. Our Sun is a middle-aged star. It formed about 4.6 billion years ago, and it has roughly 5 billion years of hydrogen burning remaining in its core. When that hydrogen runs out, the Sun will undergo a transformation. Its core will contract under gravity, while its outer layers expand. Dramatically, catastrophically, swelling to hundreds of times its current size. This expanded phase is called the red giant stage, and during it, the Sun will likely engulf Mercury and Venus, and may even consume the Earth. Whether Earth is swallowed or merely scorched depends on details of stellar physics that are still subjects of active research. But either way, the Earth as a living world, a world with liquid water, with a functioning atmosphere, with any of the conditions we associate with the planet we live on, will not survive this process. The red giant Sun will make the inner solar system uninhabitable in ways so profound that the word uninhabitable barely begins to describe it. After the red giant phase, the outer layers of the Sun will be gently expelled into space, drifting outward as a cloud of gas called a planetary nebula. The name is misleading. It has nothing to do with planets. It was coined before astronomers understood what these beautiful, glowing clouds actually were. What remains at the center, after the outer layers have drifted away, is the Sun's exposed core. A dense ball of carbon and oxygen, roughly the size of Earth, but with about half the mass of the Sun, glowing white-hot from the heat of compression. This is a white dwarf. It is not a star in the traditional sense. There is no more fusion occurring inside it. It is simply a very hot, very dense object, slowly radiating its stored heat into space. And it will do this for a very, very long time. Here is the crucial fact for our story. White dwarfs have planets. Not always, not universally, but the evidence for planets orbiting white dwarfs, surviving the death of their parent star, has been accumulating for decades, and it has become one of the most fascinating areas of modern astronomy. The question of which planets survive stellar death is not a simple one. It depends on where in the solar system the planet originally formed, how massive the star was, how the mass loss during the red giant phase proceeded, and a number of other factors that vary from system to system. The inner planets, those closest to the star, are generally doomed. Mercury and Venus, in our own solar system, will almost certainly not survive the Sun's red giant phase. Earth's fate, as mentioned, is uncertain. Mars, being farther out, has a better chance of surviving as a physical body, though it will be severely baked and almost certainly lose whatever thin atmosphere it currently possesses. The outer planets, Jupiter, Saturn, Uranus, Neptune, are the more likely survivors. Their distance from the Sun means they will not be engulfed. And while the Sun's red giant expansion will drive enormous changes in the dynamics of the solar system, altering orbital periods, possibly destabilizing some orbits through the mechanisms of mass loss, the giant planets have a reasonable chance of persisting as physical objects into the white dwarf era. What they will become, however, is a different question entirely. Without the Sun's current warmth, Jupiter, today the largest planet in the solar system, a swirling world of hydrogen and helium storms, with an atmosphere deep enough to swallow entire planets, will continue to exist, but will enter a state of profound cold. It will radiate its own internal heat for a while, as it does today, but that internal heat, too, will eventually dissipate. Jupiter will become, over billions of years, something colder and more compressed. A dark, dense ball orbiting a slowly cooling white dwarf in a system that has lost everything that once made it warm. And the white dwarf itself will be cooling slowly, patiently, radiating heat at a rate so glacial that even across billions of years, it remains observable. Eventually, over a timescale measured in the hundreds of billions of years, a white dwarf will cool from its initial surface temperature of perhaps 100,000 degrees down towards something approaching the temperature of the cosmic microwave background, roughly 2 degrees above absolute zero. At that point, it will no longer emit enough light to be visible. It becomes what cosmologists call a black dwarf. But here is something remarkable. No black dwarf has ever been observed, not because we haven't looked, but because the universe is not old enough for any of them to exist yet. The oldest white dwarfs in the universe, those formed in the very earliest stellar generations, are still cooling. The time required to produce a true black dwarf exceeds the current age of the universe by orders of magnitude. This means that white dwarfs are, in a very real sense, time capsules. Every one we observe is a remnant of a star that died before us, still in the process of cooling toward a fate that the universe has not yet witnessed. The planets that orbit them are in an interesting position. Orbiting a cooling object in an increasingly cold universe, they are gradually becoming something different from anything we normally mean when we use the word planet. We are now entering the first major epoch of the far future, a period that cosmologists have called the degenerate era, though some prefer the simpler term, the age of white dwarfs. This era begins, roughly, when the last of the ordinary hydrogen-burning stars, the red dwarfs, finally exhaust their fuel. Red dwarfs are the most common type of star in the universe. They are small, cool, and extraordinarily frugal with their hydrogen, where a star like the Sun has a lifespan of about 10 billion years. A red dwarf of modest size can burn for 1 trillion years or more. The smallest red dwarfs, objects barely above the mass threshold required for fusion, may persist for 10 trillion years. This means that the night sky as we know it, filled with the light of billions of stars, will not remain familiar for anything close to astronomical time. Most of what we think of as the stellar universe will already be dark, long before the last red dwarf burns out. By the time we reach cosmic decade 14, 10 trillion years from now, the universe will be a much quieter place. Galaxies that once blazed with hundreds of billions of stars will be populated primarily by stellar remnants, white dwarfs, neutron stars, black holes, and the cold, dead brown dwarfs that never quite succeeded in igniting fusion at all. But there will still be some light. The last red dwarfs will still be burning, Their glow will be faint and very red, shifted toward the infrared, cooler and dimmer than any star currently in the sky. And around them, planets will still be orbiting. The last red dwarf systems will be the last truly warm places in the universe. What kind of planets orbit red dwarfs? We have been studying this question intensely for the past few decades, and the answers have been both encouraging and strange. Red dwarf planets exist in abundance. We know this. The majority of exoplanets discovered by missions like Kepler and TESS orbit red dwarf stars, simply because red dwarfs are so common and so easy to observe in certain ways. Some of these planets, orbiting in the habitable zone of their dim parent stars, have been among the most exciting candidates for potentially life-bearing worlds. TRAPPIST-1, a red dwarf just 39 light-years away, hosts at least 7 planets, 3 of which orbit in or near the habitable zone. But red dwarf planets face challenges that planets around Sun-like stars do not. Red dwarfs are frequently active, prone to powerful flares that bathe their nearby planets in ultraviolet and X-ray radiation. Red dwarf habitable zones are close to the star, which means planets there are likely tidally locked, keeping one face permanently toward the star and one face permanently in darkness. These are strange worlds, nothing like Earth, and whether life of any kind could persist on them remains one of the great open questions of modern astronomy. For our story, however, the question of life is not the primary concern. What matters is this. When the last red dwarf finally exhausts its hydrogen and transitions through its own red giant phase, a quieter, cooler version of what our Sun will undergo, what happens to its planets? The red dwarf, having burned through its fuel, will exhale its outer layers in a gentle stellar wind. What remains will be another white dwarf, cooler and smaller than the one left by a sun-like star, but the same kind of object in principle. And its planets, those that survive the transition, will settle into orbits around this new cold remnant, beginning a new phase of existence. These are the worlds that will inherit the far future. Let us try to picture the universe as it will appear during the late white dwarf era. Perhaps 100 trillion years from now, a cosmic decade 14 or slightly beyond. Imagine looking out into a universe of extraordinary darkness. The great spiral galaxies, the Milky Way, Andromeda, and the rest of what was once the local group will by this point have merged into a single, larger elliptical galaxy after a collision process that will begin in a few billion years. This merged galaxy will have exhausted most of its star-forming gas long before this point. New stars are no longer being born in any significant numbers. The light that exists in this universe is different from what we know. Where our night sky shows a tapestry of colors, the blue-white blaze of young massive stars, the yellow warmth of sun-like stars, the faint red glow of the oldest and coolest. The night sky in this era will be dominated almost entirely by the dim infrared glow of cooling white dwarfs, and here and there, the last fading embers of the final red dwarfs. It is not total darkness, not yet, but it is darker than anything a human has ever experienced. Darker than the darkest corner of the current universe. Because the sources of light are so sparse and so faint, and around these fading white dwarfs, planets persist. They are cold, without a young star to warm them. Even the closest orbiting planets receive far less energy than Earth receives from the Sun today. The white dwarf, cooling from perhaps 50,000 degrees in its early life down toward 20,000, then 10,000, then cooler still, provides progressively less warmth. Planets that once had liquid water, had there been any, would have long since frozen over. Atmospheres, if they existed at all after the turbulent transition from ordinary star to white dwarf, would be thin and frigid. But these are still planets. They have mass, they have solidity, they occupy space, they orbit. The physics of being a planet does not require warmth. It requires only that an object has sufficient gravity to pull itself into a roughly spherical shape, and that it orbits something. Both conditions are satisfied. These cold worlds orbiting cooling white dwarfs are the immediate ancestors of the last planet. But they are not the last planet itself. For that, we need to follow what happens next. And what happens next is stranger than any of what we have discussed so far. Here is a concept that is easy to state, but difficult to fully absorb. On cosmic timescales, even the arrangements of matter that seem permanent are temporary. Planetary orbits are stable, but not forever. The reason has to do with a phenomenon called orbital decay, and it operates through mechanisms that are too weak to measure over human lifetimes, but which, given sufficient time, reshape the architecture of solar systems completely. One such mechanism involves gravitational interactions. Planets in a multi-planet system are constantly pulling on one another. These interactions are tiny, barely detectable even with our most sensitive instruments in most cases. But they are cumulative. Over enormously long timescales, they can cause orbits to shift in unpredictable ways. Some planets may be nudged into slightly different paths. Some may be ejected from their star system entirely, becoming rogue planets drifting free in interstellar space. Others may be gradually drawn closer to the central white dwarf. There is also the phenomenon of gravitational wave emission. When any mass orbits another mass, general relativity predicts that the system will radiate energy in the form of gravitational waves. Ripples in space-time. For close binary stars, this effect is strong enough to measure and has been confirmed in multiple systems. For planets, the effect is incomparably weaker, but given enough time, and in the far future, time is the one resource that exists in essentially unlimited supply. Even this tiny effect accumulates over spans measured in cosmic decades 20 and beyond. Gravitational wave emission will cause planetary orbits to decay. Very slowly, extraordinarily slowly, but inexorably. Planets will spiral inward, imperceptibly, toward the white dwarf they orbit. Most of them will, eventually, fall in. This is the slow catastrophe of the long future. The gradual dismantling of solar systems through the combined effects of gravitational interactions and gravitational wave emission. It takes an almost incomprehensible amount of time. For an Earth-sized planet in an Earth-like orbit around a white dwarf, the timescale for orbital decay via gravitational wave emission alone is something like 10 to the power of 80 years, a number so large it dwarfs even the boldest estimates for the lifespan of protons. But in a universe that may have unlimited future time, even this is not infinite. But there is another process that operates on a different level entirely. A process that attacks not the orbit of a planet, but the substance of the planet itself. We have been talking about the death of stars, the cooling of white dwarfs, the decay of planetary orbits. All of these are processes that are either confirmed or strongly theorized based on well-established physics. But now we need to venture into territory that is more speculative, though not unreasonably so. The standard model of particle physics which describes the fundamental building blocks of matter and the forces between them, predicts that protons, the positively charged particles at the center of every atomic nucleus, are stable. They do not decay. A proton left alone will remain a proton indefinitely. But the Standard Model may not be the complete picture. Many extensions of the Standard Model, grand unified theories that attempt to incorporate the strong nuclear force, the weak nuclear force, and electromagnetism into a single framework, predict that protons are not truly stable. They decay, extremely slowly, but they decay. The simplest grand unified theories predict a proton lifetime of somewhere around 10 to the power of 31 years. Experimental evidence has ruled this out. We have built enormous underground detectors specifically to watch for proton decay and have not yet seen it. This means the proton lifetime, if it is finite, is longer than the simple models predict. Current experimental limits place the proton lifetime above approximately 10 to the power of 34 years for certain decay modes. But for our story, the possibility of proton decay, even if it happens on timescales of 10 to the power of 40 or even 10 to the power of 100 years, is significant. Because if protons decay, then all matter composed of protons, which is all ordinary matter, including every rock, every ocean, every mountain, every planet in the universe, is ultimately temporary. Given enough time, a solid planet would dissolve. Proton by proton, atom by atom, its substance would transform into lighter particles. Positrons, neutrinos, photons. The energy would disperse. The solid object would, over an almost immeasurable span, simply cease to exist. If protons decay, then no planet can survive to the ultimate end of the universe. But the planet that lasts longest, the last one to have dissolved, is still, in a meaningful sense, the last planet that existed. And the question of which planet that would be is a question of which world is composed of the most protons, which is roughly equivalent to asking, which surviving world will be the most massive? This is where the story narrows to a single extraordinary object. Among all the categories of planet, gas giants occupy a special place in the story of the very far future. And among gas giants, there is a particularly important class of object that deserves careful attention. We typically think of planets and stars as different things, and they are. But the boundary between them is not as sharp as it might seem. Stars fuse hydrogen. Very large gas giants do not fuse hydrogen. But they are, in their basic composition and structure, not entirely unlike the smallest stars. They are mostly hydrogen. They are held together by gravity into a roughly spherical shape. They radiate some heat from their interiors. As the universe ages and the temperature of everything gradually approaches zero, something interesting happens to gas giants. They change, very slowly. The hydrogen in their interiors, subjected to enormous pressure, transitions over vast timescales into different configurations. Under the extraordinary pressures, deep in the interior of Jupiter-sized worlds, hydrogen exists in a metallic state. Electrons are stripped from their atoms and move freely through the material, the way electrons move through a conductor. At these pressures, the planet is not a ball of gas in any simple sense. It is a dense, metallic quantum object, and over time scales reaching toward cosmic decade 22 and beyond, the most massive gas giants will undergo a further transformation. The material in their interiors, metallic hydrogen subject to extreme quantum pressure effects, will begin to behave differently from anything we encounter in ordinary physics. Through a process related to quantum tunneling, the hydrogen in their deepest interiors may gradually transform into something else. Something heavier, something denser. The gas giant, over incomprehensible timescales, transforms into a solid ball of iron. This is not an instantaneous process. It is not dramatic. It is not an explosion or a collapse. It is the slowest possible transformation. The gradual rearrangement of matter from one configuration to another, atom by atom, through the statistics of quantum mechanics. But given enough time, a Jupiter-sized gas giant will become a cold, dark, solid sphere of iron, approximately the size of Earth. These iron planets, the transformed remnants of the universe's largest gas giants, are the most durable solid objects that the laws of physics appear to permit. They are dense, they are chemically inert in the environment of a cold, dark universe. They are held together by the electromagnetic force in an extremely stable configuration, and they orbit white dwarfs whose own cooling has proceeded so far that they have become essentially black dwarfs, cold, dark, and nearly invisible, of all the candidates for the last planet in the universe. The massive iron worlds that were once gas giants are the most credible, and the most massive among them. The one that takes the longest to dissolve through proton decay, if proton decay occurs, is the one that earns the title. The last planet. Let us think about what other candidates might exist for the title of last surviving planet. Rocky planets. The Earth-like worlds composed primarily of silicates and iron are durable, but they are less massive than gas giants. Less mass means fewer protons, which means faster complete dissolution if proton decay is the ultimate fate of matter. Rocky planets will dissolve before gas giants. The Moon, Mars, any rocky world in any solar system, all of them will be outlasted by the great iron spheres that were once gas giants. Neutron stars are different objects, not planets in the conventional sense. They are supported by neutron degeneracy pressure, not chemical bonds. If protons in their compressed form behave differently from protons in ordinary matter, their fate may differ, but they are generally excluded from the category planet because they are, in a real physical sense, the remnants of stars rather than worlds that formed around stars. Brown dwarfs, failed stars that never ignited fusion, are another interesting case. They are more massive than gas giants, but less massive than stars. They, too, will cool and eventually transform into iron spheres through the same quantum tunneling process, but on slightly different timescales. Some classification systems would not call these objects planets, even after their transformation. The most straightforward claim to the title of last planet belongs to the most massive surviving gas giant in the universe. A world that was once perhaps many times the mass of Jupiter, that orbited a relatively long-lived star, that survived its parent star's death to enter a stable orbit around a white dwarf, and that then, over unimaginable timescales, was transformed by quantum mechanics into a cold, dark, solid iron sphere, drifting in an almost lightless universe. It will be, by any reasonable definition, a planet. It will be solid. It will have mass. It will occupy space. It will be, in the vast darkness, the last piece of solid ground in existence. We have been following the logic of stellar death and planetary survival, but we have not yet paused to truly picture the universe in which this final world exists. Let us do that now, because the picture is one of the most extraordinary things that scientific reasoning has ever produced By the time the last gas giants have completed their transformation into iron spheres, which begins to occur around cosmic decade 25 or so, the universe is profoundly different from what we know. Let us take inventory. The ordinary stars are gone, all of them. The hydrogen-burning stars, the helium-burning giants, the white dwarfs, even the cooling remnants of stars. All have faded past the point of emission. The last actively cooling white dwarfs will have become black dwarfs somewhere around cosmic decade 17 to 20. Though the timeline is uncertain because it depends on assumptions about the efficiency of heat radiation in the far future. The galaxies are gone, not destroyed exactly. The matter they contained still exists. But the gravitational dynamics of systems containing large numbers of objects ensure that, over cosmic decade 19 or 20, galaxies will have dissolved through the gradual ejection of stars. Via gravitational interactions, most of the mass ends up scattered. Individual stellar remnants, black dwarfs, neutron stars, black holes, drifting through intergalactic space, separated by distances so enormous that galaxy ceases to be a meaningful concept. The black holes that were once at the centers of galaxies, the supermassive black holes, the most massive objects that stars can produce, are the dominant structures in this era. Sagittarius A, the supermassive black hole at the center of the Milky Way, has a mass of about 4 million solar masses. The largest known supermassive black holes are billions of solar masses. In the far future, after the galaxies have dissolved, these objects will still be there, slowly accreting whatever sparse material drifts close enough to fall in. But even black holes are not eternal. Stephen Hawking demonstrated theoretically that black holes radiate energy through a quantum process now called Hawking radiation. The rate of this radiation is inversely proportional to the mass of the black hole. Larger black holes radiate more slowly, and the timescale for a supermassive black hole to evaporate completely via Hawking radiation is approximately 10 to the power of 100 years. This is called a googol of years. Even this number, the googol, is not the last chapter, but it is the end of the era in which the universe contains any of the structures we would recognize from our current universe. By cosmic decade 100, the last black holes have evaporated into a diffuse fog of particles. Where does this leave our last planet, the iron sphere? If proton decay has not already dissolved it, exists in a universe containing almost nothing except itself. A few other cold, dark objects scattered over incomprehensible distances, a diffuse background of photons and neutrinos, and the cosmic geometry of expanding space-time. If protons do not decay, the iron planet may survive even the evaporation of black holes. It would drift through a universe containing no stars, no galaxies, no black holes, no light sources of any significance. A universe in which the only energy is the extremely faint thermal radiation of objects at temperatures, mere fractions of a degree above absolute zero, and the even fainter glow of Hawking radiation during the long Argo black hole era, now so redshifted by cosmic expansion as to be spread across wavelengths longer than the current observable universe. This is the universe in which the last planet lives its final existence. Not a universe of fire and chaos, not even a universe of darkness, as we understand darkness. A universe of almost absolute stillness, where matter exists but barely matters, where space persists but nothing moves at any significant speed, where time continues to pass but has, in every experiential sense, stopped. There is something we have not yet fully resolved. The last planet, as we have described it, must be orbiting something. A planet, by definition, is in orbit around a star or stellar remnant. But what will it be orbiting in the extreme far future? Its original parent star, the white dwarf that the gas giants spent the early portion of its far future existence orbiting, will have become a black dwarf long before the gas giant completes its transformation into an iron sphere. The black dwarf will still be there. It will still have gravity. The planet will still orbit it. But orbital dynamics, as we discussed, involves slow decay. Gravitational wave emission will gradually shrink the orbit. Over spans of cosmic decade 80 and beyond, assuming the planet survives, the orbit will have decayed substantially. The planet may be in a much closer orbit than it originally maintained. It may, eventually, be very close indeed to the black dwarf. Does it fall in? Eventually, perhaps. But the time scale for an iron planet in a typical orbit to decay through gravitational wave emission into a black dwarf is itself so large that it may exceed the time scale for proton decay, making the question somewhat academic. Which process wins? Orbital decay or matter dissolution? Depends on which of these two timescales is shorter, and both involve numbers that are genuinely at the edge of what physics can reliably calculate. What we can say is this: the last planet and the black dwarf it orbits are companions in the dark, locked together by gravity, slowly drawing closer. In the deep future, they are the only solid objects within what was once the Milky Way, perhaps the only solid objects within the former local group. They orbit each other with a patience that makes the current age of the universe look fleeting. The black dwarf does not warm the planet. It cannot. It has no heat left to give. It provides only one thing: gravity. The planet holds to it the way a frozen moon holds to a burned-out sun. Not because of warmth, because of physics. There is a question that has been hovering, unasked, throughout this journey. A question that every person listening to this has probably been turning over quietly. The question of life, not whether the last planet supports life in its final form. It almost certainly does not, in any form we would recognize. But the deeper question: is life possible anywhere in the universe during any of the eras we have been discussing? And if so, when does it end? The answer depends on how broadly we are willing to define life. Life as we know it, life built on carbon chemistry, liquid water and solar energy, has a relatively near-term deadline. The conditions for this kind of life become progressively harder to maintain as stars cool and the universe ages. The habitable zones of the last red dwarfs will persist for trillions of years. And there are researchers who have seriously proposed that the long, quiet era of red dwarf stars might actually be the most hospitable period in cosmic history for life. Not our brief early chapter of sun-like stars, but the much longer later epoch of stable, long-lived red dwarfs, bathing their planets in just enough warmth to maintain liquid chemistry. But even this extended habitable era ends. When the last red dwarf expires, the window for carbon chemistry life closes. From that point onward, the conditions required for biology as we understand it, liquid water, chemical gradients, the right temperatures for molecular reactions, are gone. The universe does not suddenly become inhospitable in a violent way. It simply becomes too cold. The chemistry that life runs on requires temperatures above the freezing point of water, and no part of the universe will reliably maintain those temperatures after the last star dies. What about more exotic forms of life? Physicists including Freeman Dyson, explored the question of whether intelligence and complexity could persist into the deep future using non-biological substrates. Could minds constructed from magnetic monopoles or from computer processes running on increasingly cold hardware persist into the extreme future by thinking more and more slowly, taking more and more time between each thought, conserving energy while maintaining coherence? Dyson's calculations suggested it might be possible, at least in principle. More recent analysis by Lawrence Krauss and Glenn Starkman suggested the answer was no, that the thermodynamics of an accelerating universe would eventually prevent such strategies from working indefinitely. The honest answer is that we do not know. The physics of the extreme deep future involves uncertainties that current science cannot fully resolve. What we can say is that by the era of the last planet, in the remote reaches of cosmic decade 40 and beyond, if matter persists that long, the universe is so cold, so sparse, so close to thermodynamic equilibrium, that any process resembling thought, experience, or activity of any kind faces its barriers that appear, on current understanding, to be insurmountable. The last planet, in the most probable version of the far future, is not home to anything. It is not even being observed. It is simply there, drifting in the dark, the final solid thing, surrounded by an almost perfect and absolute stillness. We have come far enough in this journey to pause and attempt something that is, strictly speaking, beyond the reach of language, to describe what the universe of the last planet actually feels like. Not for the planet, planets do not feel, but for any hypothetical observer who might somehow exist there. Begin with the sky. There are no stars. There has not been a star, in any meaningful sense of the word, for longer than the current age of the universe, multiplied by numbers that quickly become absurd. The light that a hypothetical observer could see, if they looked in any direction, would be the extremely faint, extremely red-shifted afterglow of processes that concluded unimaginably long ago. The cosmic microwave background, already faint and cold in our era, would be so profoundly red-shifted by billions of years of cosmic expansion that its wavelength would exceed the diameter of the current observable universe. It would be, in any practical sense, undetectable. The sky would be dark, not the dark of a cloudy night, where the absence of visible stars is a temporary condition waiting to be reversed by the clearing of clouds, not the dark of a moonless night in a wilderness far from city lights. A different kind of dark entirely. A dark that is the permanent, structural condition of everything. A dark that is not the absence of light, but the completion of a process. The universe having radiated away the majority of its energy over timescales that make the concept of a very long time seem quaint. The temperature of this environment would be incomprehensibly close to absolute zero. The cosmic background temperature in our current era is about 2.7 degrees Kelvin. As the universe expands, this temperature decreases. By the era of the last planet, the background temperature of space will be so close to absolute zero that the difference is essentially undetectable with any instrument. The planet itself, the iron sphere that was once a gas giant, will be at this temperature too. It will not be merely cold the way a frozen planet is cold. It will be cold at the quantum mechanical level, where the thermal vibrations of atoms have slowed to near stillness. The metal will be in a state called a quantum solid. Its atoms arranged in a crystal lattice, with an almost total absence of thermal disorder. It will be quiet, quieter than anything in the current universe. Sound requires vibrating matter, and the vibration of matter requires energy. On the surface of a planet at near absolute zero temperature, in a universe with no atmospheric medium to transmit pressure waves anyway, there would be a silence so complete it would be indistinguishable from the silence of absolute nothing. Everything we have explored so far has been, in a sense, preparation. The physics of stellar death, the survival of gas giants, the transformation of hydrogen into iron over incomprehensible timescales. All of it has been leading to a single question that now stands before us like a door. Is matter stable? This is not a philosophical question. It is a physics question, and the answer to it divides the fate of the last planet into two completely different stories, not similar stories with different endings. Two stories so different from each other that they describe universes that share almost nothing except their origin. If matter is stable, if protons do not decay, then the last planet will survive indefinitely. It will drift in the dark for timescales that make even the googol years of black hole evaporation seem brief. It will exist in a universe that has become something so alien to our intuitions that physicists have struggled for decades to find adequate language for it. And eventually, not through dissolution, but through the subtlest possible physical process, even it will be gone. But the manner of its going will be unlike anything we have discussed. If matter is not stable, if protons do decay at some rate and on some time scale, then the last planet has a different kind of deadline, a more definite one. The iron sphere that was once a gas giant will slowly dissolve, proton by proton, over spans that still exceed the current age of the universe by factors of billions, but it will dissolve. And the last moment of the last planet will be the moment its final proton decays into lighter particles that disperse into the ambient near nothingness of the deep universe. Let us follow both paths, because each one reveals something important, not only about the fate of matter, but about the nature of the universe itself. Picture the iron planet at cosmic decade 37. The black hole era is ending. The largest supermassive black holes are completing their Hawking evaporation, each one departing the universe in a brief burst of high-energy particles that disperses almost instantly into the surrounding emptiness. The universe is crossing a threshold. For the first time in its history, the dominant objects in existence are not black holes, not stellar remnants, but simply cold matter. Iron planets, black dwarfs, the occasional neutron star, scattered across a space that has expanded so enormously that the average distance between these objects has grown to scales that dwarf even the current observable universe. In this era, the proton, if it does decay, has been decaying for longer than any process we have previously discussed. A planet's worth of iron is approximately 10 to the power of 57 protons, give or take orders of magnitude. If each proton has a lifetime of 10 to the power of 40 years, then the planet is losing protons at a rate that, when averaged over the entire object, is measurable, in the sense that some non-zero number of protons are decaying per year. But the number is so small relative to the total that the planet, in any year or any century or any millennium, appears perfectly solid. The decay rate is so low that it would take 10 to the power of 40 years for the bulk of the planet to dissolve. What does proton decay look like in the unlikely event that we could observe it? A proton, depending on the mechanism, decays into a positron and a neutral pion. which itself immediately decays into 2 gamma-ray photons. These gamma rays travel outward from the decay site and are absorbed by the surrounding ion, heating the material infinitesimally. The positron almost immediately finds a nearby electron because iron has plenty of electrons, and the two annihilate each other into 2 more gamma-ray photons. The result is a tiny, invisible flash of radiation that dissipates into the surrounding material as heat. Not dramatic, not visible, not even, in any practical sense, detectable against the background, but real. Each proton that decays removes a small amount of mass from the planet permanently. The energy from its decay is briefly radiated outward. This means the last planet, if protons decay, is a very faint source of energy. In a universe that has almost no other energy sources, in an era when even the Hawking radiation of black holes has ceased, the iron planet glows, very faintly, from the interior heat generated by proton decay. Not enough to warm its surface meaningfully. Not enough to produce visible light. A faint trickle of energy in an almost perfectly cold universe. And over cosmic decade 40, one followed by 40 zeros in years, the planet shrinks. Imperceptibly, year by year, century by century, millennium by millennium, atoms vanish from its interior as their constituent protons decay. The planet does not develop holes or cracks or surface features from this process. The decay is evenly distributed throughout the material, removing mass at a uniform rate from every part of the object simultaneously. The planet simply becomes, over unimaginable spans, slightly less massive, slightly smaller, slightly less present. By the time the last proton in the planet decays, at approximately cosmic decade 40, depending on the actual proton lifetime, the planet no longer exists. Not destroyed in any conventional sense, not fallen into something or absorbed by something, simply dissolved over a span of time so enormous that the dissolution was, in any practical sense, undetectable in progress and only meaningful in retrospect. The last proton decays. 2 gamma-ray photons are produced. They travel outward through what was once the surface of the last planet, into a universe that contains, now, no solid matter of any kind. The photons redshift as they travel. They become lower and lower in energy. They will never be absorbed because there is nothing left to absorb them, and that is the end of matter. If protons decay, but what if they are not? What if the proton is truly, fundamentally, permanently stable? Not because of any approximate symmetry or near conservation law, but because baryon number conservation is exact and eternal. Then the story of the last planet takes an unexpected turn. Without proton decay, the iron sphere that was once a gas giant persists. Cosmic decade 40 passes. Cosmic decade 50. Cosmic decade 60. The universe continues to expand. It becomes colder. The Hawking radiation of the last black holes has long since dissipated. The background temperature of space approaches, asymptotically, absolute zero. It never quite reaches it. Thermodynamics prevents perfect zero from being achieved. But the difference between the actual temperature and zero becomes smaller with each passing era. The iron planet drifts. It has by now, almost certainly, spiraled into an orbit extremely close to the black dwarf that is its companion. The 2 objects form a binary system, a cold, dark pair, locked in an embrace maintained by nothing but gravity, drifting through a universe that has otherwise become, to a very good approximation, empty. Does anything happen to them? Here is where the physics becomes deeply strange. and where the confidence of our predictions decreases significantly. We are now in territory where theoretical frameworks exist, but observational confirmation is impossible. These processes have never occurred and will never be observed by any civilization that might arise in our current era. But the physics, insofar as we understand it, suggests that things do still happen on timescales so large that even the cosmic decade notation begins to strain. One such process is quantum tunneling. At the level of quantum mechanics, matter does not simply sit still the way macroscopic intuition suggests. Every atom in the iron sphere has a tiny but non-zero probability of tunneling through energy barriers that classical physics would declare impassable. Over spans of time measured in cosmic decades 65 and beyond, 10 to the power of 65 years, the iron in the planet will spontaneously reorganize its crystal structure through quantum tunneling. More significantly, quantum tunneling allows nuclear reactions to occur without the temperatures normally required to overcome the Coulomb barrier between nuclei. Given enough time, even at temperatures near absolute zero, the iron nuclei in the planet will fuse with one another through quantum tunneling, seeking out configurations of even lower energy. Iron is already at the minimum of nuclear binding energy. You cannot extract energy from iron through either fission or fusion, which is why iron is the endpoint of stellar nucleosynthesis. But iron-56, the most common isotope, is not quite the absolute ground state of nuclear matter under all conditions. Some theoretical work suggests that, given unimaginably long timescales, quantum tunneling would cause the iron in the planet to slowly convert into nickel-62, which has a very slightly higher binding energy per nucleon than iron-56. This transition would happen atom by atom, tunnel by tunnel, over spans reaching toward cosmic decade 65. The planet of iron would gradually become a planet of nickel. The change would be imperceptible in any given era. The two metals are chemically similar, physically similar, structurally similar. But over the relevant timescale, the composition would shift. This is not dissolution. The nickel planet is still a planet. It still has mass, still has gravity, still occupies space. The protons within it are still there. The matter has simply reorganized into a slightly lower energy configuration. But even this is not the most remarkable process that awaits the stable matter planet. Let us return to the companion of the last planet, the black dwarf, the cold remnant of the star that once gave the gas giant its solar system home. Over cosmic decades 20 through 80, the orbit of the planet around the black dwarf has been decaying through gravitational wave emission. The process is imperceptibly slow. Each year, the orbit shrinks by a distance that no instrument could ever measure. But across cosmic decade 80, 10 to the power of 80 years, the orbit has decayed substantially. The planet is closer to the black dwarf than it was. Much closer. And something interesting happens when the planet draws close enough. Black dwarfs, as we have discussed, are the cooled remnants of white dwarfs, themselves the remnants of ordinary stars. They are, in terms of their composition, primarily carbon and oxygen in a crystalline lattice, held in a state of extraordinary density by electron degeneracy pressure. Their mass is roughly half the mass of their original star. For a star like the Sun, the resulting black dwarf would have roughly half a solar mass, roughly 500 times the mass of Jupiter. This object, despite having no light to emit and no activity to speak of, has something important. gravity. And as the iron planet spirals inward over cosmic decades 60 through 85, it will eventually reach a point where the fortresses of the black dwarf, the differential gravitational pull across the diameter of the planet, exceed the gravitational self-cohesion of the planet itself. This boundary is called the Roche limit. When the planet crosses inside the Roche limit, it begins to be torn apart. Not in an instant. Tidal disruption is a process that unfolds over thousands of orbital periods at minimum. The planet elongates. Material from its near side, where the black dwarf's gravity is strongest, begins to flow toward the black dwarf. The planet stretches. It develops a tidal tail. Over time, in this context, time measured in millions to billions of years, which is an eye blink by the standards of the era. The planet is pulled apart into a ring of material, orbiting the black dwarf. And then, gradually, this material spirals inward as orbital decay continues. Eventually, it falls into the black dwarf. The black dwarf accretes the iron. This addition of mass heats the black dwarf's surface very slightly, if the mass is sufficient. If the original star was large enough that the black dwarf remnant is close to the Chandrasekhar limit, the maximum mass a white dwarf or black dwarf can support, then the accretion of the planet's mass might push the black dwarf over that limit. What happens when a black dwarf exceeds the Chandrasekhar limit? This is an area of active theoretical investigation. And the answer is both violent and strange. The object can no longer support itself against gravitational collapse through electron degeneracy pressure. It collapses, and depending on the exact composition and circumstances, this collapse may trigger a thermonuclear explosion, a type Ia supernova. But this would be a supernova in a universe that contains no interstellar gas, no nearby stars to witness it, no observers of any kind. The explosion would expand outward. The shockwave would travel through a nearly perfect vacuum, meeting essentially nothing. The light, gamma rays, X-rays, visible photons, would travel outward and redshift over cosmic time into radio waves, and then into wavelengths longer than anything in our current universe, and eventually into something that no physics we know can fully characterize. It would be the last dramatic event in the history of matter. A lonely explosion in a universe that has, for all practical purposes, already ended. And if the masses do not cooperate for this final drama, if the black dwarf and the accreted planet together fall short of the Chandrasekhar limit, then the end is quieter. The planet's material merges with the black dwarf. The combined object settles, and then nothing more happens. Two pieces of cold matter have become one. The planet is gone. Not dissolved, not radiated away, but absorbed, incorporated into a larger cold object that will persist in the same near-absolute stillness it has maintained for the previous many cosmic decades. We have been describing these events with a certainty of language that deserves, at this point in the documentary, a moment of honest examination. Can any of this actually be observed? Not by us, not by any civilization arising in the current era of the universe. The timescales involved are so remote that any attempt to observe the far future directly is simply impossible with current or foreseeable technology. We cannot send probes to cosmic decade 40. We cannot wait out cosmic decade 85 in any vessel or station. The universe we inhabit, warm, stellar, active, is a brief opening chapter that provides no windows into what follows. What we have instead is logic, the laws of physics as we currently understand them, extrapolated forward across timescales they were never empirically tested against, generating predictions that are internally consistent, but that may turn out to be wrong in ways we cannot anticipate. Perhaps the laws of physics change on cosmic timescales. Perhaps dark energy, the force driving the accelerating expansion of the universe, will behave differently in the deep future than current models predict. Perhaps structures and phenomena arise in the extreme far future that no current theory anticipates. The honest position of the physicist is not certainty. It is the more interesting claim. Given what we know, this is what appears to be implied. And what is implied is striking enough that it deserves to be taken seriously. The last planet is not a guaranteed prediction. It is the product of careful extrapolation, of following the known physics of stars, planets, nuclear matter, and quantum mechanics into a domain where no measurement has ever been made. The picture we have assembled is the most internally consistent story that current physics can tell about the far future of solid matter. And it is, by any measure, a remarkable story. We have been talking about the last planet as though it were a unique object, the specific world that will, at a specific moment in the far future, be the last solid thing in existence. But there is a deeper way to think about what the last planet represents. Not as an individual object, but as a symbol of something about the universe itself. Consider what it means that the universe will have had a last planet at all. The universe began in a state of almost perfect uniformity. A hot, dense plasma that was, on the large scale, extremely smooth. Over the first few 100 million years, gravity amplified tiny fluctuations in this uniformity into structures. The first stars, the first galaxies, the first planetary systems, the universe went from a smooth plasma to a rich, complex structure filled with stars and planets and, in at least one case, life. This process of complexification, the universe becoming more structured, more varied, more interesting, required the right conditions. It required the right laws of physics. It required that gravity be attractive and that matter be able to clump. It required that nuclear physics work in a way that produced stable atoms with rich chemical behavior. It required that the expansion of the universe proceed at a rate that allowed structures to form before everything dispersed. All of this, from a physicist's perspective, is not mysterious. It follows from the initial conditions and the laws. But it is, from a philosophical standpoint, remarkable. The universe went out of its way, so to speak, to be interesting. And now consider the far future. The process of complexification is not permanent. Gravity, which built the structures of the universe in its youth, eventually has the opposite effect, pulling structures together into black holes, contributing to the dissolution of galaxies, eventually assisting the decay of orbits. The universe that gave rise to stars and planets, and the chemistry of life, gradually moves toward a state of lower and lower complexity. The last planet is the final artifact of the universe's complex phase. It is the last remnant of the era in which matter organized itself into structures more intricate than a uniform gas or a black hole. When it is gone, whether through proton decay, tidal disruption, or quantum processes operating over cosmic decades beyond easy comprehension, something has been lost that will not be recovered. The universe will continue to exist. Space will continue to expand. But there will be nothing in it that could serve as the ground for any of the processes we associate with the interesting universe. No surfaces for chemistry, no gravitational wells for orbits, No density contrasts for anything to form. The last planet is not simply the last planet. It is the last word in the longest sentence the universe has ever written. There is a concept in physics called the Poincare recurrence theorem. It states that a dynamical system with certain properties, a finite energy and a finite volume, evolving under reversible dynamics, will, after a sufficiently long time, return arbitrarily closely to any previous state. The time required for this return is called the Poincare recurrence time. And for a system as large and complex as the observable universe, it is almost unimaginably large. Something like 10 to the power of 10 to the power of 118 years for a realistic estimate. The existence of this theorem has led some physicists and philosophers to suggest that, given infinite time, the universe might spontaneously reconfigure itself into any state, including a state resembling our current universe, or a state containing a single planet orbiting a star, or a state containing a civilization, not through any directed process, but through random fluctuations of whatever remains after all ordinary structures have dissolved. This idea is associated with the concept of the Boltzmann brain, a hypothetical observer that might coalesce randomly from quantum fluctuations in the far, far future, existing briefly as a coherent conscious entity, before dissolving back into equilibrium. The physicist Ludwig Boltzmann, in the 19th century, grappled with whether the order we observe in the current universe might be itself just such a fluctuation within a larger eternal chaos. These ideas are genuinely entertained by serious physicists, but they come with significant caveats. The timescales involved in Poincare recurrence are so vastly larger than even the timescales we have been discussing, that they represent a qualitatively different kind of consideration. The time for the last planet to dissolve through proton decay, 10 to the power of 40 years, is itself dwarfed by the Poincare recurrence time by a factor that numbers cannot adequately convey. More importantly, the expanding universe may not satisfy the conditions of the recurrence theorem. If space continues to expand, driven by dark energy, then the universe does not evolve in a finite volume. It expands without bound. And for a system evolving in an expanding space, the recurrence theorem does not straightforwardly apply. There may be no recurrence. The far future of our universe may be a one-way journey into a lower and lower complexity state. Not a cycle, not an oscillation, but a monotonic approach toward a final condition of complete thermodynamic equilibrium. The universe on this view does not reset. It simply ends, not in a dramatic final moment, but in the asymptotic approach to a state of absolute sameness, where nothing can change because nothing has the energy to drive any change. The last planet is not, on this view, a prelude to a rebirth. It is one of the last events in a story that has no sequel. There is a thought experiment that has been floating behind everything we have discussed, and now is the time to engage with it directly. Suppose, hypothetically, that an observer could be present on the surface of the last planet. Not a human. The conditions are incompatible with any biology we know. Not a robot or machine in any conventional sense. The timescales required would demand energy sources and maintenance cycles that the far future cannot provide. But a hypothetical observer, purely for the purposes of exploring what perspective might be possible from this unique location. What would such an observer know? They would know if they had access to records or reasoning. that they were on the last solid ground in the universe. They would know that the cold, dark sphere beneath them had once been a gas giant, a world of swirling hydrogen storms and metallic interiors, orbiting a star that once shone. They would know that this star was itself born in the early universe, in a generation of stars that formed before the Milky Way had fully assembled its current structure, the material in the planet, the iron, the nickel, the quantum crystal lattice that makes up every square meter of its surface, would carry in its atomic structure the history of every star that processed its constituent matter. Every iron atom in that planet was forged in the interior of a dying star. Every heavy element was produced by stellar nucleosynthesis or supernova explosions, or in some cases by the violent merger of neutron stars. The last planet, despite its barrenness and its cold, would be a record of cosmic history written in atomic structure. The observer would look up and see nothing. The sky would be empty of every light source visible to any human who has ever lived or ever will live. The last black hole evaporated long ago. The last white dwarf cooled long before that. There are no galaxies, no star clusters, no nebulae, nothing that shines in any wavelength. But the observer would know, if they had the knowledge and the instruments, that the darkness was not the absence of history. It was the completion of history. Every photon that ever radiated from every star that ever burned has been traveling outward since the moment of its emission. Some of those photons, emitted by stars in the early universe, are still traveling, redshifted now beyond any practical detection, spread thin across wavelengths longer than anything we know, but still moving, still real, still carrying the information of the moment of their emission. The universe, in the era of the last planet, is a place where the past exists only as inference, and the present is nearly indistinguishable from perfect nothingness. But for an observer with perfect knowledge, every feature of the cold, dark landscape would be a clue to everything that came before. The iron beneath their feet was once a sun. We have not yet fully addressed one of the most significant variables in the story of the far future: dark energy. Dark energy is the name we give to whatever is responsible for the observed accelerating expansion of the universe. In 1998, two independent teams of astronomers studying distant supernova explosions discovered, to their considerable surprise, that the expansion of the universe is speeding up rather than slowing down. Gravity, acting on all the matter in the universe, should be decelerating the expansion, pulling everything back, even if not enough to cause a recollapse. Instead, something was pushing. Some energy inherent in the vacuum of space itself, distributed evenly throughout the cosmos, was driving the expansion to accelerate. We still do not understand what dark energy is at a fundamental level. The simplest mathematical description, a cosmological constant, a fixed energy density of empty space, fits all current observations reasonably well, but it provides no insight into where this energy comes from or why it has the value it does. What dark energy does to the story of the last planet is significant. Because of dark energy, the universe does not merely expand. It expands at an ever-increasing rate. This means that distant objects are accelerating away from us. It means that, beyond a certain distance, the cosmic event horizon, no signal sent today could ever reach us, and no signal sent from beyond that horizon could ever reach us either. The observable universe is not merely large. It is shrinking, in the sense that the region from which we could ever receive information is getting smaller as time passes. For the far future, this means that the last planet, wherever it ends up, in whatever remnant structure persists, is essentially in isolation, not merely far from other objects, but causally disconnected from them. Whatever happens elsewhere in the universe cannot affect it. Whatever happens to it cannot affect anywhere else. The accelerating expansion has turned the universe into a collection of causally isolated islands, each one drifting into its own private dark future. This adds a dimension to the existence of the last planet that goes beyond mere physical isolation. It is not merely far away from other things, it is cut off from them permanently, in a way that is encoded in the geometry of space-time itself. The last planet exists in a bubble of space that is expanding away from all other bubbles, accelerating, with no possibility of reconnection. There is something in this image that resists easy description. A world that is not merely alone, but alone in a way that is geometrically final. Every story has a last event, a final moment after which nothing more occurs. For the universe, identifying the last event is a surprisingly complex problem. It depends heavily on which physical theories are correct, which processes operate on the longest timescales, and what counts as an event in a thermodynamically nearly equilibrium universe. If protons decay, the last event is the decay of the last proton anywhere in the universe. After that, there is no ordinary matter. Only black holes remain, and then they too evaporate. The last event among black holes is the evaporation of the most massive one, which occurs around cosmic decade 100. If protons are stable, the last event, involving ordinary matter, may be the quantum tunneling of the last pair of black dwarf nucleons into a configuration of lower energy, a process so slow that it makes proton decay look hasty. Or the last event might be quantum fluctuation related. In a universe approaching absolute thermodynamic equilibrium, quantum mechanics does not permit perfect stillness. There will always be fluctuations, tiny random variations in energy density that occur because the uncertainty principle demands it. These fluctuations do not create lasting structure. They arise and dissipate almost instantly. But they are real, and they represent a kind of ongoing activity in an otherwise inert universe. The last event, on some theoretical frameworks, would be the last such quantum fluctuation, large enough to be meaningfully distinguished from the background. The last moment when the universe did something, however briefly, that differed from perfect uniformity. After that last event, the universe would be in a state that physicists sometimes call the heat death. Not a hot death, despite the name. The term refers to the thermodynamic concept of heat, specifically the equilibration of temperature. In heat death, the temperature everywhere is identical. Nothing flows from anywhere to anywhere else, because flow requires a temperature gradient, and there are no temperature gradients left. Nothing changes because change requires a difference in energy from one place to another, and there are no such differences left. This is the final state, not nothing. Space-time persists, quantum fields persist, the universe in some technical sense continues, but nothing ever happens again. The last planet existed before this final state. It was, in some sense, the last reason for things to happen. When its protons decayed, or when it was tidally disrupted into the black dwarf, and the combined system reached equilibrium, the universe lost one of its last departures from perfect uniformity. It came closer to heat death. And then, eventually, over processes even more subtle and remote, it arrived. The last planet was not the cause of the universe's death, but its disappearance was one of the last chapters of the universe's life. Here is something that often goes unnoticed in discussions of the far future of the universe. The story of the last planet teaches us something about the beginning. We started this documentary on a planet, one that is currently warm, wet, surrounded by a middle-aged star, orbiting in a galaxy that is itself relatively young. We live in what might be called the golden age of planets, an era when star formation is still ongoing, when new planetary systems are still being assembled, when the conditions for solid worlds with surfaces and atmospheres are broadly available across the cosmos. This golden age is brief in cosmic terms. The era of freely forming stars, the era in which we currently live, spans only a few trillion years. After that, star formation ends. After that, the universe enters the long, quiet decline we have been describing. We exist at what appears to be an early moment in the total history of the universe. The universe is, on any reasonable projection of its total timeline, extraordinarily young. 13.8 billion years is a significant span of time by any human measure, but placed against even the conservative estimate of the total future duration of matter, 10 to the power of 40 years. If proton decay operates, it is less than the first breath of what follows. This observation has a name in philosophy and cosmology: the temporal mediocrity argument, sometimes called the doomsday argument in certain formulations. If all moments in the history of the universe are in some sense equal, if intelligent observers are no more likely to exist in one era than another, then we should expect to find ourselves somewhere in the middle of the typical observer's timeline. But we appear to be very near the beginning of the total cosmic timeline. This could mean various things: that the conditions for observers are uniquely favorable in the current era compared to the far future, or that intelligent life is necessarily brief, or that the far future contains no observers to speak of, making us genuinely early in the total census of self-aware beings. Whatever the reason, we are here now, in the warm, bright, early universe, surrounded by stars and planets and the richness of a cosmos still actively producing complexity. And we are asking questions about a cold, dark, isolated world that will drift through a universe that has forgotten complexity was ever possible. There is something remarkable about that asymmetry. It means the universe produced beings capable of reasoning about the last planet far before the last planet exists. The universe gave rise to minds that can imagine its own ending. And this happened near the very beginning of the story, not near the end. Whatever that means philosophically, it is a fact worth sitting with. We have been thinking about the last planet as though it were a single deterministic object, the inevitable product of a chain of physical reasoning that leads to one specific world. But the reality is more interesting and more poignant than that. We do not know which specific planet will be the last. We do not know which solar system, which gas giant, which composition of matter will win the competition of survival. The last planet is, from the perspective of our current knowledge, anonymous. It exists somewhere in the future, in a solar system that may already exist or may not yet have formed, around a star that is still burning, or perhaps not yet ignited. It might be a gas giant in a solar system we have already discovered. Perhaps Kepler 7b, a Jupiter-sized world, orbiting a star somewhat larger than our Sun, about 1,000 light-years away. Perhaps one of the 7 planets in the TRAPPIST-1 system. If a gas giant lurking at greater distances around that red dwarf survives the star's eventual death, perhaps a world we have not yet found, orbiting a dim red dwarf in a region of the galaxy that our surveys have not yet reached. More likely, the last planet orbits a star that is not currently known to us. Perhaps a star that has not yet formed. One of the last stars to condense from gas in a galaxy that still has a little star-forming material remaining long after most stars have died. This star will burn for trillions of years. A dim red dwarf barely above the hydrogen fusion threshold. And around it, the planets that form will be the last planetary system in the universe, the last solar system, the last collection of worlds with any hope of being called a neighborhood. One of those worlds, the most massive gas giant among them, will survive the death of that final star. It will settle into orbit around the resulting white dwarf. It will cool over billions of years into an iron sphere. And then, in the darkness that follows everything else, it will be the last planet. We will never know its name. We could not give it one even if we tried, because any name we gave would be a name attached to a designation we cannot make. We cannot point to it now. It is either not yet formed or not yet discovered, and its discovery would require being present at a time so remote from now that the concepts of discovery and we would need considerable rethinking. But it is out there. In the logic of the physics, it is waiting. If we could travel to the last planet, not in a physical spaceship, but in imagination, equipped with perfect knowledge of its composition and history, what would we find there? We would find, in the iron crystal lattice of the planet's interior, a record of every stage of the universe's history that contributed to its existence. The hydrogen at the core of the gas giant that this planet once was. Hydrogen that condensed from the primordial gas of the Big Bang, that formed the star this planet orbited, that was returned to space when that star died, and was eventually incorporated into the next generation of star formation that produced the last stars. Carries within its atomic structure the signature of the original nucleosynthesis. The iron that the planet has become was produced in the death throes of earlier stars, whose remnants were recycled through the interstellar medium across cosmic timescales. Every atom in the last planet has a biography. The iron was fused in stellar interiors billions or trillions of years ago. The star that produced it exploded, scattering the iron as part of a supernova remnant that expanded through the interstellar medium for millions of years before being swept up into the gas cloud that eventually collapsed to form the last star and its planets. The planet inherited this iron from the death of a star that died in the active universe before the long decline set in, and the hydrogen, if any remains, locked in crystal structures within the planet, is itself some of the oldest matter in existence. Hydrogen forged in the first 3 minutes after the Big Bang, unchanged across the entire history of the universe, is present throughout the cosmos. Some of it ended up in this planet. In that hydrogen, there is a direct physical thread connecting the first moments of existence to the last solid world. The last planet is not merely a cold iron sphere. It is a physical archive of cosmic history. Everything that happened, every star that burned, every supernova that scattered material across a galaxy, every planetary system that formed and eventually dissolved, contributed through a chain of cause and effect that could theoretically be traced to the existence of this particular world. This is true, in some sense, of all matter. Every atom carries its history, but in the context of the last planet, the final artifact of the universe's complex phase, the idea takes on a resonance that is difficult to dismiss as mere sentiment. This world is the last place where the universe's history is inscribed in physical form. When it dissolves or falls into its companion, that inscription disappears forever. We are near the end of this journey, and there is a question that deserves to be asked directly. Why did the universe make planets? Not how. We understand the how in broad outline. Gravity causes gas to collapse, stars form, material remaining after stellar ignition settles into a disk. And from that disk, through the gradual accretion of dust and planetesimals, planets assemble. The mechanism is understood. The why is a different question. And it can be asked in two different ways, depending on one's philosophical commitments. The first way: what is the physical function of planets? What role do they play in the economy of the universe? In this sense, the answer is relatively clear. Planets are repositories of rocky and icy material that did not make it into stars. They are formed by the same gravitational processes that form stars. They represent the universe's tendency to organize matter into structures at every scale available, from the largest galaxy clusters down to the smallest dust grains. The universe makes planets because physics, operating through gravity and thermodynamics, produces them as a natural consequence of the processes that form stars. The second way, the why, can be asked is more interesting. Is there any sense in which planets matter? Is there any sense in which the universe's production of planets across billions of years and billions of galaxies adds up to something? For any universe that gives rise to life, and ours has given rise to at least one example of life, perhaps more, the answer seems to be yes. Life, as we know it, requires planets. It requires surfaces, atmospheres, oceans, geological activity, the interplay of chemistry and energy and physical structure that only a planet seems to reliably provide. Stars are not suitable as homes for biology in any form we know. Black holes certainly are not, but planets, warm, rocky, diverse, with the right chemistry and the right proximity to a modest star, are the environments in which matter can organize itself into the extraordinary complexity of living systems. The universe made planets, and planets made life possible. And life has given rise to minds that can look up and ask the original question. That chain of causation, from quantum fluctuations in the early universe to hydrogen clouds, to stars, to planetary systems, to chemistry, to biology, to consciousness, is one of the most remarkable things we know about the cosmos we inhabit. And at the very end of that chain, long after the final mind has gone dark, the universe still has one planet left. Not warm, not life-bearing, not complex in any meaningful chemical sense, but present, persistent. The last expression of a universe that spent its entire productive life making worlds. We have arrived, at last, at the moment we have been approaching across this entire documentary. The last proton in the last planet decays, or the last iron atom in the last planet tunnels into the black dwarf that was once its companion, or the last quantum fluctuation in the dissolving material of the last ant planet radiates outward into a universe that contains, now, only the uniform sea of particles and fields that quantum mechanics permits at absolute thermodynamic equilibrium. The planet is gone, and what remains? Space-time remains. The geometry of the universe, The fabric on which everything else is written persists. It is expanding, driven by dark energy at an accelerating rate. It will continue to expand for as long as dark energy exists. And current evidence suggests dark energy is not going away. The universe will expand forever. Fields remain. Quantum fields permeate all of space-time. The electromagnetic field, the gravitational field, the fields associated with every elementary particle. These fields are not nothing. They carry energy, specifically the zero-point energy required by quantum mechanics, the irreducible minimum below which no quantum system can be pushed. These fields fluctuate. They will always fluctuate. Even in perfect thermodynamic equilibrium, the quantum fields that fill space-time are alive with virtual activity at the smallest possible scales. But these fluctuations do not produce anything lasting. They arise and vanish, conserving energy over tiny timescales. They do not create planets or stars or atoms. They are, in a sense, the universe breathing, an involuntary mechanical activity that continues even when everything has long since gone still. There may also be something else, something we do not yet understand. Dark energy is real. We know this from observation, but we do not know what it is. It may be a fixed property of the vacuum, unchanging forever. It may be a dynamic field that evolves over time. It may be something entirely different from what current models suggest. The universe of the far future may hold surprises that our current physics cannot anticipate. This is not a weakness in our reasoning. It is an honest acknowledgement of where knowledge ends and the unknown begins. We have followed the logic of current physics as far as it will carry us. Beyond that, we must acknowledge that the map has an edge. The last planet existed at the edge of that map. Beyond it, we have only the fog of genuine uncertainty. Before we leave this subject, let us take a moment to stand back and appreciate the scale of the journey we have made. We began at the present moment, 13.8 billion years into the history of a universe that began in a hot, dense, featureless plasma and gradually organized itself into the complex cosmos we inhabit. We surveyed the death of ordinary stars, the survival of planets, the transformation of gas giants into iron spheres, and the long decline of the universe's active phase. We moved through cosmic decade 14, when the last stars die, and cosmic decade 17 through 20, when the last white dwarfs cool into black dwarfs. We passed through cosmic decade 37, when black holes evaporate and the last non-matter structures disappear. We arrived at cosmic decade 40, when, if proton decay operates, the last planet dissolves into radiation. The number 10 to the power of 40 years is worth trying to feel, even if it resists comprehension. The current age of the universe is 10 to the power of 10 years. 10 to the power of 40 is a billion times larger than that. If each year in the history of the universe so far were itself a universe of the same age, and then you repeated that process again, and again, and again, the cumulative time would not approach cosmic decade 40, and yet cosmic decade 40 is not the end. It is, in some sense, the early middle of the story of matter, if matter is stable. The processes of quantum tunneling and orbital decay, and eventually Poincaré recurrence, if that applies at all, extend to timescales that make cosmic decade 40 look like an opening act. We are tiny. Our civilization is tiny. Our species is tiny. The span of recorded human history, roughly 5,000 years, is to the age of the universe what a single second is to the age of the universe. And the age of the universe is to the lifetime of the last planet what a single second is to the age of the universe. This nesting of scales, this extraordinary depth of time, is one of the most distinctive features of the universe we inhabit. We did not expect it. When early scientists began to extend their understanding of the cosmos into the past, the timescales they encountered were repeatedly larger than anything previously imagined. The same is true of the future. The universe is not merely old, it has barely started. There is a tradition in the better kind of science documentary, one that this program has tried to honor, of not ending with only the facts, of pausing near the conclusion of a long journey to ask what the journey means, not to lecture or to preach, but to sit quietly with the implications of what has been described and allow the weight of it to settle. We have spent this time traveling to the last planet. We have followed it from its origins as a gas giant orbiting a dying star, through its transformation into an iron sphere, through the long darkness of a universe that has progressively extinguished every other light, to its final dissolution or its final merger with a cold companion. It is a cold story. In some interpretations, a lonely one. The last planet exists in circumstances that no living thing has ever experienced, and, in all probability, no living thing ever will. It is cold beyond any cold we know. It is dark beyond any dark we know. It is old beyond any age we can genuinely feel. And yet there is something in this image that resists the conclusion that it is merely bleak. The last planet is made of atoms. Those atoms were forged in stars. The stars that forged them burned for billions of years, warming planetary systems, enabling the chemistry of clouds and oceans and weather, and, in at least one case, life. The iron in the last planet once passed through the interior of a star. It was assembled into a planet by the same gravitational processes that assembled the Earth. It orbited a star, a modest star, perhaps a dim red dwarf, that shone for trillions of years. And somewhere in the history of the universe, perhaps early in the warm, active era we currently inhabit, or perhaps later, in the long twilight of the red dwarf stars, there may have been life on other worlds made of the same kinds of atoms. There may have been minds that looked up at their own night sky, wondered about the cosmos they inhabited, perhaps asked some version of the same questions we are asking tonight. The iron in the last planet does not know any of this. The last planet itself has no experience, no memory, no awareness of what it represents. But we know. We exist at a moment early enough in the universe's history to still have the energy and the light to ask the question and follow it to its end. That is not a small thing. The universe made beings capable of understanding the universe. It did this early, near the very beginning of its productive phase, in a warm and energetic era, when the conditions for complexity were exactly right. It gave rise to minds that could look forward across the incomprehensible span of cosmic time and describe, with reasonable accuracy, what the last moments of solid matter will look like. And the last planet, cold and silent and alone at the edge of the universe's ending, has no idea that somewhere in its deep past it was seen, that it was thought about, that it was given a name, the last planet, by creatures who lived and breathed and wondered on a warm, rocky world orbiting a young yellow star in the early years of a universe that had barely begun. We have reached a place where honesty requires acknowledgement of what we do not know. We do not know if protons decay. decades of experimental effort have not detected a single proton decay event. The proton may be stable on timescales that exceed the current age of the universe by hundreds of orders of magnitude, or the proton may be unstable, with a lifetime just beyond the reach of our current detectors. The answer to this question changes the story of the last planet significantly. We do not know the ultimate nature of dark energy, the cosmological constant, the simplest explanation for the accelerating expansion. Fits current data well, but alternatives have not been ruled out. Some alternatives predict that dark energy will eventually cause the expansion to accelerate so rapidly that even atomic nuclei are torn apart in a big rip scenario. Others suggest dark energy will weaken over time. The behavior of dark energy on cosmic timescales is not known. We do not know whether quantum gravity produces effects on these long timescales that our current theories do not anticipate. General relativity and quantum mechanics are incompatible at a fundamental level. We do not have a complete quantum theory of gravity, and the physics of the extreme far future may be dominated by effects that this missing theory would describe. We do not know whether life, consciousness, or complexity, in some form we cannot currently imagine, might persist into the deep future, by means that current physics does not predict. All of these unknowns are genuine. They are not gaps to be papered over with speculation. They represent the actual frontier of human knowledge about the cosmos. What we have described in this documentary is the best story that current physics can tell. It is a story derived from solid observational astronomy, confirmed nuclear physics, well-tested quantum mechanics, and the validated frameworks of general relativity and thermodynamics. Where we have ventured into speculation, proton decay, quantum tunneling transformations, we have labeled it as such. The honest scientist's position is not certainty, but rather the conviction that the best available framework, applied carefully and with acknowledged uncertainty, gives us a genuine window into the deep future. The last planet is not a certainty. It is an honest extrapolation. And it is, by any measure, one of the most extraordinary extrapolations that the human mind has ever produced. Let us end where this documentary has always been going, quietly, from the very first moment. Not with the iron sphere in the dark, not with the math of proton lifetimes or the physics of tidal disruption, but with something simpler. Tonight, wherever you are, the sky above you contains light, the stars you can see, the few thousand visible to the naked eye, a tiny sample of the hundreds of billions in the Milky Way, are all burning. Every one of them is, right now, fusing hydrogen in its core, radiating energy outward, warming its planetary system, providing the conditions for whatever chemistry or biology or geology or weather might be happening around it. The universe is right now in the middle of its most productive era. Stars are being born. Planets are forming. The interstellar medium is rich with complex molecules, the building blocks of biology, drifting between stars on timescales of millions of years. The cosmos is active, warm by cosmic standards, still making new things. The last planet already exists, almost certainly, somewhere in this universe. It is not yet the last planet. It is just a planet orbiting a star, unremarkable among the billions of similar worlds we have catalogued, and the many more we have not. It does not know its future. It has no more awareness of what it will become than the hydrogen atom in the early universe had of the star it would one day help to burn. But the logic of physics connects this moment to that one. The same laws that govern the fusion in the sun's core govern the fate of every star that will ever burn. The same gravity that holds the moon in orbit around the Earth will, trillions of years from now, hold the last iron planet in its decaying orbit around a black dwarf. The same quantum mechanics that governs the chemistry of life on Earth will, in the extreme deep future, govern the tunneling transitions that transform the last gas giant into the last solid world. We are part of this story. We are not separate observers watching the universe from outside. We are made of the same atoms that will, in some form, persist into that dark future. The iron in our blood was forged in dying stars, just as the iron in the last planet will be. The hydrogen in our water is primordial hydrogen, forged in the Big Bang, unchanged in its fundamental nature from the first 3 minutes of existence. The universe is not separate from us. We are one of the things it has made in this warm and early era, with the energy and the complexity and the time that its active phase has provided, and we have used some of that energy in this brief window to follow the universe's story forward. Past the death of stars, past the cooling of white dwarfs, past the evaporation of black holes, to the cold and lonely iron world that will be the last piece of solid ground before the lights go out completely. There is something worth carrying from this journey. Not fear. The far future is too remote and too abstract to justify fear. Not despair. The universe's eventual stillness does not diminish the extraordinary richness of what it has already produced, and what it will continue to produce for trillions of years to come. What is worth carrying is something closer to perspective. We exist in the brief, warm, luminous chapter of the universe's history. We exist at a time when the sky is full of stars, when planets are abundant, when the conditions for life and thought and curiosity and wonder are available in a way that will not persist forever. The universe gave us this window, this warmth, this ability to ask questions and follow them wherever they lead. The last planet will not have any of it. It will have only the dark and the cold and the slow tick of quantum processes in a universe that has moved on. But we have this, right now, tonight. The light from the stars is still falling on us, and we are still here to see it.